Very nice.
Okay.
We will continue this lecture. Okay, so I want to recall what we did last time. We did uh, talk about compactness, and we showed that continuous image of a compact set is compact. And we also showed that continuous image of a connected set is connected. So continuous functions preserve compactness and connectedness. The idea that continuous function preserves connectedness is what is called the intermediate value theorem in in calculus in general. So here it is. What is that intermediate value property is what we'll do. Intermediate value theorem. Okay, so if I have a function AB to R, AB is a metric space anyway, to R is maybe instead of if, let's say let F be continuous. Okay. What we see really is that if I have a continuous function defined on the interval A to B, and if it has to sort of go maybe like that, it doesn't matter. There is this Y, and here is the A, and here is B. This is F of A, and this is F of B. So if you take any number psi between, essentially that's what we want to prove that, AB is a connected set, so F of AB is a connected set in R. Because the connected set in R is an interval. So F of A to F of B becomes an interval there. And so for every, right? So if it's continuous, if I take a number, maybe L is a real number, and F of A is less than equal to L is less than equal to F of B, then any value I take between FA and FB, this is the intermediate value, that L will be achieved by some C. Okay. Then there exists some X naught, or maybe X naught, I can call that X naught in AB, such that F of X naught is equal to L. I think proof is quite easy because this AB is a connected subset of R, and the continuous function preserves connectedness, so F of AB is connected. Okay, connected means it's an interval. Right? Once it is an interval, and in that interval, so F of AB is an interval. And in that interval, I have taken FA and FB. So naturally, the FA and FB are in this. Therefore, the interval FA to FB is actually contained in I, right? That means that is in the range. Okay, therefore, that's what it is. Since AB is connected, so is F of AB. And we already proved that any connected set in real line is a interval. So is F of AB equal to I, F of AB. But any connected set in R is an interval. In R is an interval. We mentioned that before. Therefore, F of AB is an interval in R. Now, right away, since FA, therefore, I can directly say FA to FB, that is contained in I, and we are done. And you have taken element L is in this. So L is then in FA to FB implies L is in I. Implies L is in I. I is the range. So therefore, there exists a X naught in I in the domain AB such that f of X naught equal to L. Right? There exists X naught in domain AB such that f of X naught is L. We're done with the intermediate value theorem. Okay. Similarly, it's actually one of the properties of the continuous functions. If we teach them.
So this is on real line. We prove it in the for any metric space.
Oh, yeah, we can do that as long as right hand side is a real line, right? So right hand side is connected is what is important here, right? So we can do that. Yeah, I'm sure I agree with that. Okay, as long as R is there. So I take a number between FA and FB. I have to have a premise. I think a connected subset will be good enough here if you want. Of a metric space is good enough and R there. Okay.
If it is necessary for our complex variable, then we will go for it. Otherwise, just we leave it.
It has to be R on this side. This side connected set is okay. Because here the problem is I'm taking a number between FA and FB, and that should be contained in L. In I. Okay. So the I is an interval. That is why there is no gap between FA and FB. That there is no gap between FA and FB is what I am using here. Okay. You don't jump. If there are gaps here, then you have to jump and still maintain continuity. So what you are saying, I will just do that. So instead of this, I have just a connected set here and R there. Still, I can write the theorem. Right?
If we make on the right side, if we change from R to something else, then we'll have to have, instead of calling it as an interval, we should call it as a connected subset, which is basically right. Like on the right side, if we make it R square, then we'll have to make it as a connected subset.
There is a bit of a problem here. No. I don't want to say that. I want R only here on the right hand side. You have no escape. I'm saying something in between FA and FB. Okay. Actually, if you take a X to Y and this is the range it is onto, for every Y there is a premise. Right? That's not the point. The point is if a function, continuous function, takes a real value here and a real value there, it has to connect, have every value between the two things. That's what I'm trying to say in this. So at best, if you want, I will write another theorem for you. I will write another theorem. Let's see that if it works out now. Okay, let X be a connected metric space. And F be a function from X to R continuous. Okay. Let X1 comma X2 belong to X, and L is any number between Fx1 X2. L lies between Fx1 and Fx2. R is connected and therefore it's an interval. So the range will not be disconnected is what I want to say. That means once I say it is not disconnected in the right hand side, it's connected in the right hand side, it is an interval. And therefore you cannot have a function, broken like this. That's what we're trying to say. Okay, then there exists x naught in x such that f of x naught is L. That's all I can say. Okay. What we are saying is continuous function has this property. If instead of that, if I take the domain is also a real line, and if a continuous function goes from a particular level to a level, it can go any way you like, but it has to not be broken. Okay. But whereas if I have taken a function f, let's say from some domain to R, yeah. For example, I have taken a function from AB union CD. Here, there another CD here. And I can have a function like this, which is broken here. And it's possible I do not have to be able to take. I have gone from here to here, and there are values in between which are not having pre-images. This is what we are trying to say. Okay?
Right.
So this is not nice. This is true, but the previous theorem is what I want there. Okay? Continuous functions, for example, R to R continuous functions. If I look at, a closed interval AB to R, I have taken a continuous function, suppose. Okay. I want to say it has two properties. One of them is the connectedness. Because this is connected, the image is connected, and therefore every value in between any two values of the function, between FA and FP, I take a value L, I have a pre-image. Okay. Other thing is existence of extrema. Existence of maximum minima for this function will be achieved. Okay, if this set is compact. If the set is not compact, the function need not have maxima or minima. Okay, if you have a function defined on, let's say, something like maybe 0, maybe let's say minus pi by 2 to pi by 2. It's an open interval to R. If I take fx equal to tan x, this is going to go minus infinity to infinity. It has no bounds. But if the domain is a compact set, then it has to have bounds. Not only that, the bounds will be achieved. I want to write that theorem here. Next theorem is about that. Okay. Another theorem is like let okay fx to R be continuous. And K is a compact subset. X is compact. Then there exists maybe x naught and y naught in y such that, okay, f of x naught is equal to supremum of f of x, where x is in K. So as x ranges in K, f of x has some kind of a bound. So therefore, f of K has bound, and that bound is also achieved. And f of y naught is equal to infimum of all fx, x is in K. Okay. So continuous function achieves, first of all, it's on a compact set. If you look at the image, what is that? K is a compact set, F is continuous, so F of K is compact, subset of R. And therefore it's closed. In any N cell, a compact set is closed and bounded. So F of K will be closed and bounded. I hope you are done. We'll see that. F of K is compact in R. Therefore, F of K is closed and bounded. right? Because it's bounded, the supremum is finite. Therefore, alpha equal to supremum of all fx, x in k. That is actually supremum of fk, right? That's what it is. Is finite. Not only that, you're talking about supremum. That means there should be sequence which converges to alpha. So there exists a xn in k such that f of xn converges to alpha as n to infinity. But this sequence exists in the compact set, right? So which is sequentially compact. So it has a convergent subsequence which converges to some point. Since k is compact, there exists a subsequence xnk of xn which converges. Say to some x naught. Okay. So then what happens? It's a continuous function. Another thing I know is that because xnk converges to that, f of xnk converges to f of x naught because f is continuous as n tends to infinity. Okay. And there you go. That is your alpha. Okay. Only thing x naught actually, this converges where? This sequence converges in k. Say to k in x naught in k. F of xn converges to f of x naught. So I found an x naught in k such that f of x naught equal to infimum of all that. Right? That's it. This completes the proof of the first part.
Okay, you can use the bound, I mean, closedness also.
Yeah. Yeah. Sure. F of k is compact. And so this convergence is what? This f of xn converges to this boundedness I used already, that alpha is finite.
Closedness.
Okay.
Closeness.
Closedness. Okay. Yeah. Did I use that or not? First of all, closedness. Closeness is there because finally I found out the alpha is. I didn't use this specially. Okay. I didn't use this specially, but that's what it is. Fk is closed and bounded. First of all, boundedness said this is finite. And first of all, by the very definition of this is supremum, I can find what is this? This alpha is supremum. Where x is in this. So there's a sequence xn in the compact set k, so that f of xn converges to alpha. Closeness says alpha is also in f of k. That's a difference. I didn't bother to say that.
Oh.
And it's clear. You see, closeness is also clear, but I didn't use it specially. F of xn converges to alpha as n tends to infinity. Xn has a subsequence which converges to x naught in k. So f of xn converges to f of x naught, and that's what it is. So therefore, alpha equal to f of x naught. That's what I wanted to prove.
Oh.
That is actually closeness, if you want to say. Because where is alpha? In fk.
Okay.
But I didn't use it specially.
Yeah, because the sequence converges to alpha. That alpha
Converges to x naught, and so f of xn converges to f of x naught. That means it converges to this converges to actually alpha, and so there it is. There you go. So alpha is f of x naught, and the same argument goes for that. So the essence of this is if I have a continuous function on a compact set, definitely the bounds f of k will be bounded, and the bounds of f of k are achieved by the function f at points in k. That's the essential argument I want to tell.
We use another word, f attains its bounds.
Yes, f attains its bounds. f of k is bounded and it has its infimum and supremum. Those are achieved by the function f. They're attained by the function at some places x naught and y naught. Okay.
Within that.
Rest of the argument follows this thing. I don't have to say it. Okay. For infimum also same argument. So we can proceed. Then we introduce what is called uniform continuity. Continuity at a point, continuity on a set, and uniform continuity. What is continuity at a point? We said F is from a metric space XD1 to another metric space omega D2. We said it's a continuous at some point. It is continuous at some x naught. It means what? Means for every epsilon greater than 0, there exists a delta greater than 0, such that distance between x and x naught is less than delta. X is in the space x, implies distance between fx and fx naught is less than epsilon. And continuity at every point on x means it's continuous on x. Yeah. So continuity at each point corresponding to each epsilon provides a delta, but the delta might depend on the x naught as the definition goes.
If delta is uniform, that is uniform continuity.
If the delta does not depend on the specific x naught, then it becomes uniform continuity. So here is the definition of uniform continuousness. Okay. Let f be a function from the metric space xd1 to omega d2. Okay, we say f is uniformly continuous. F is uniformly continuous on x when if for every epsilon greater than 0, there exists a delta greater than 0, such that for x and y in x, okay, distance between x and y less than delta implies distance between fx and fy is less than epsilon. Uniform, that's what it is. Okay. What we will notice is that if the domain is compact, the continuity on that compact set actually implies uniform continuity. That is the theorem we want to prove. So if okay, here is the next theorem. Let XD be a compact metric space. If f from, of course, omega is that there. If x to xd1 to omega d2 is continuous, then it is uniformly continuous. Continuity implies uniform continuity if the domain is a compact set. Okay. Oh, well, I think we can easily prove that. Not a big deal. Compactness argument actually will finish this. Okay, let's see. Let epsilon be greater than 0. Okay. At each point, f is continuous. So at each point, I can find, okay, for each x in x, there exists a delta that may depend on x positive, such that distance between y and x is less than delta x would imply a distance between fy and fx is less than epsilon. Let's put epsilon by 2. If necessary, I'll change it to epsilon by 2 or anything down the line. Okay. Now, therefore, all these balls centered at x and delta x, x in x becomes an open cover for x. For capital X. Is that right? Okay. And x being compact, it admits a finite cover. Since x is compact, you see now the importance of the compactness. Okay, you don't need that many balls. Finitely many of them will really do this job. Since x is compact, there exists x1, x2, and so on, xn in x. Okay, such that union ball centered at xk delta xk uh, uh, k equal to 1 to n will be the entire x. Now you see, I have infinitely many deltas probably, and their minimum will not exist. But here I have only finitely many deltas. Their minimum exists. So let's take delta to be minimum of delta xk, 1 less than k less than n. Then delta is positive. Okay. Now we will achieve what we want. Take any x and y in x, and suppose the distance between x and y is less than maybe delta by 2. Okay. Delta by 2 or delta by 3. Or, yeah, less than delta. Maybe I should do epsilon by 3 there. Anyway, it doesn't matter. Less than delta, that's good enough. Yeah, less than delta by 2. So what happens is x and y are covered by this thing there. So I should be able to find some xk in that, which is near to x and nearer to y, both because delta by 2, right? I can find an x. This x will be in some ball around some xk. This y will be in ball around some other xk dashed. But these two are too close. So both of them will lie in a ball around some, okay, xk, right? X is going to be in a ball around xk
Right.
of distance uh, delta. And y and is going to be in some other xk dash in a ball around of delta. But I see that these two things are very close by. I think I can clearly say, therefore, there exists, suppose this xk dash and xk should almost, you can take them one to be the same, because these two things are too close, right? Maybe x and y are here. Okay. Okay, it doesn't matter. I want to make it come close to each other, right? Yeah, it's possible there. One is in this, one is in that. I don't want to do that. Uh, if that is the case, I don't need to do that. You see what happens? Probably one is inside, one is in that. Then I have to do some more argument,
Yeah, you have to put one more ball around that.
one more ball around and do that. I just wanted to get to one single point so that I can just finish off one line. Otherwise, because I have continuity at xk, I can continuity xk dash. Okay. Uh, uh, I didn't want to do that. Okay. Mm. Distance between fx and fy is less than equal to distance between fx and fxk, fxk and fxk dash. I didn't like that. So I should make sure my choice of the deltas and epsilon are such that I get into in the same thing. Let me think about it.
Make that as 2 delta, then this they will fall in the same thing, right?
Make that.
In dxy less than 2 times delta, but eventually we want it, then we. Mhm.
Yeah. It is the domain. I see that. I have all these balls covering the whole space X. So X is in one ball and Y is in another ball, but X and Y are too close to each other. They are actually within a delta by 2 distance. I just want to say that, yeah, within the, yes. Yeah, so that's it. That's all good. So I should do the following. I can see that. Very easy. I take half of this. I'm just cooking up some. I take delta itself, half of that. Okay,
Yeah,
and I
yeah,
make
that's
another
now
half of
now
that.
you make it. Yeah, another
They
half.
are too close to each other. So, right, I think I got it. Right, then did you get that? There exists next k. There exists a k between 1 and n.
No, even then they can be so close, that but still in 2 different balls. So you have
Yeah,
to
they can be
introduce
in
a new
different bars.
ball.
No
Yeah.
need. I will do that. So, what did I do? The distance between them is taken delta by 2. So, right? So, x is here. This is small distance. Now, here, here, yeah, there is, excuse me. What happens is, yeah, here, yeah, here itself, I should make by 2. Maybe that's what I should do that. Here itself, I should make by 2. Okay, here itself, I make small bars covering X. How about that? Huh? Here by 2 itself covers. Okay, right? This by 2 itself covers. Okay. And now, when I took these two things already within a delta by 2 distance, eh? uh, so these are here and here, these are objects. This is in some ball at a delta by 2 distance. This is xk, this is x. Eh? This is yk, and this is y. Okay. And now I have taken distance between x and y to be less than delta, less than.
No, however small you make it, that dxy less than, however small you make it, they might fall into different balls.
Yes, they do
So
fall.
close to the boundary that they might fall into different balls.
Yeah. Yeah, but the
So if
point
they,
they fall in different balls. Yes.
right. So what I was thinking is, if they are in two, if they are in single ball, then we know what to do. I mean, that problem is solved. If they are not in the in the same ball, then can we create a ball around those two things and add that to our list of xk's? And that delta will be less than the infimum minimum of that delta will be less than the delta.
Yeah,
That radius of that ball will be less than the delta anyway.
yeah, something like that you have to do. I'll come back to this one in 1 minute now. You are right.
Yeah.
These things are actually when x and y are within a what is that within a delta distance. When y is within a delta distance of x, can you hear me well? Okay. Okay.
Yeah, we can hear you.
Okay.
Yeah, I
Okay.
can hear you.
This is less than epsilon. That's good. Now, all these things are covering x. So what happened? This is a delta ball. There's a delta ball. Okay. Now x and y, even if I do make them very close, one falls into that, right? Uh, uh, so here I have this difference is less than epsilon by 2 or whatever. That distance is also less than epsilon. But I have also to worry about
Hello? Hello?
Yes, I'm listening to. Tell me.
Ah.
Actually, what I'm trying to say is that if I made these balls very small and cover X, okay, then XK and XK, YK will be small balls. So suppose I made this delta by 2, okay, then these two are already close enough. They can't be too far because they have to cover that. This is a delta by 2 distance. That is a delta by 2 distance. Now I have taken X and Y to be close to each other by delta. So X will be here, Y will be here, and how can I? But now if I take a delta ball, that will contain delta ball around XY, that will contain both XK and YK. That's what I want to say.
Yeah.
Okay, right? Then
We take a
yeah,
delta ball around x plus y by 2 that should
yeah,
cover both the
yeah,
xk ball and yk ball.
yeah. That will cover
Sorry.
because these are small balls. Okay, so D XY less than delta. So actually, X is in XK, Y is in XK dash, but somehow they both have to be inside delta ball of XK, right? Now I think the argument goes well. X and Y are within delta distance.
Oh,
Okay,
okay.
X and Y. So these balls are made very small, which is covering X, finitely many of them. So now, where is XK, X and Y? X and Y distance is less than delta. X is in this and Y is in this. Okay. And if I take from X a circle of radius delta, okay, that should contain both YK and XK. Okay. So I can choose single XK, which will be within the delta radius of X, within the delta of radius of Y. Okay. I think this is done. I just assumed it's just nothing there, and actually it's nothing. I took too much time. So what I said, there is an XK ball of radius delta by 2, in which X is there. There is another YK ball of radius delta by 2. Maybe I'm worried that it doesn't, and in which Y is there. Now, this is X and this is Y. So within the ball of radius delta around XK, this is just delta around XK. So this distance is less than delta. This distance is less than delta, but I think these two cannot be. So if around X, if I take a circle of radius delta that contains X as well as Y. So it contains XK because that is there. YK is what we are worried. Maybe Y is here and YK is here. Is that what it is? So my argument is not good. Good. Yes, sir. Yes, sir. Is that right?
Yeah, I mean but see, each of these xk and yk balls, their radius is delta by 2 we put.
Mm-hmm.
Okay. If you make that radius as delta by 4, then
Mm.
their xk and yk will be at most, I mean, x and y will be separated by at most delta.
Yeah, yeah. That's
So
what
you
I try
can
to. Yeah.
you
Then I
can
could.
build a
Yeah.
ball around x plus y by 2 with
Mm,
a delta radius that will cover both of them.
mm. But
So
I
if I
actually
make
want to cover around only. I want to use only XK and YK, or XK and XK dash only have to be used because around that I can get that. So that's so
yeah.
what I want to. Yeah, maybe delta by 4 will do. Okay, I want to choose a. I'm in trouble now. XK, a K, 1 less than equal to K less than equal to N, such that both X and Y are in B XK delta. That's what I want to do. So I want to make sure X and Y are very close to each other. If X and Y are very close to each other, I should be able to do.
But
Then distance between fx and fy will be less than or equal to distance between fx and fxk. But first of all, did I use continuity of
we didn't use that continuity property.
I have to use the
Actually, we are having compactness.
the continuity at each point is already being used. Delta fxk fxk dashed. Sorry, I will start the proof one more time. I bungled it. I just assumed it will work. His proof is probably different. I didn't bother. He used a different proof. I just said compactness has given me only finitely many. Okay. So continuity at each finitely many points has given me delta 1, delta 2, delta n, and the minimum is there. So I said if x and y are within delta distance, I should get that. Okay. I got it wrong. I shouldn't rest it there. Okay, we'll prepare a proof quickly. So,
Brother, if we choose delta in such a way that it is 4 times the minimum of that, right? Right. And then if we choose any xy in x, okay, in such a way that dxy less than delta, right? Then there has to be a ball around either xk or yk such that with a distance of with a delta by 2 ball that should contain both x and y.
that's
Because
what
I chose delta sufficiently big, 4 times of the minimum of those,
that's
right?
their x. Yeah.
So
that is the x.
that is the x, and then if you take a y,
Intentionally, I have taken this somewhere far off. So these balls can be as small as you want. You can make it 1/4 if you want. So they're
right,
small balls. So now these two are actually within a delta distance. So therefore, if I take a delta ball around it, not only does it contain this, it might end up containing this also. Yeah.
but right now you chose delta as the minimum of all those deltas.
Yeah.
Right.
If I make, I think it will work out. If you make this less than delta by 2, we are allowed to do anything you want, right? If you make this less than delta by 2, for example, then even though these are also
right.
small. Yeah.
Yeah.
So if I take a delta ball around xk, that will contain both x and y and xk dashed. Yes, that's what you should do. Then what happens is single x. That's what I'm trying to say. At the end, I want to get a single xk, which is in which in the delta ball of that xk, both x and y should land in. Right? Yes. That's what I had to do. choose an X case such that both X and Y land in that, then we're done. Okay. So I think here I should make them slightly small by 4. I mean, I'm desperate, so I'm doing all that. By 4, I make it, right? Okay. So
Yeah.
this is within a by 4 delta by 4 ball. This is within delta by 4 ball. Okay. Right. And these two may be at a delta distance. I can make it them even delta by 2 distance. I've taken minimum of that. I made this delta by 2 distance. So therefore, if at xk, if I make a delta radius ball, then both x and y will fall in that. I think that is good. Okay. Make this delta by 2. Okay. Then definitely I can choose that both of them will fall in a single delta ball. Delta is good enough, but here I use delta by 4. The balls are very small. I think this is good. Now I got it.
No, on that, when you are taking that union of balls,
Very
xk,
small radii or delta by 4.
whether you put by 4 or by 2, it doesn't matter because you are putting your delta as a minimum of those things. The one below, yeah, minimum of
I'm using minimum of these deltas.
minimum of those deltas.
Those
Okay.
deltas. I'm not using them.
Yeah.
The
Right,
ball,
right.
okay. And that
Yeah,
too, I'm so desperate. So I even put delta by 2 here.
just in case. Okay, fine.
Because I'm terrible here. Okay. Got it? Now we are okay.
Yeah.
So within that x and y are within 2k such that both x and y will lie within delta distance of that. Okay, then we're done. So now distance between fx and fy, I want to show is smaller than epsilon. You can also put epsilon by 3 or something, start with if you want. That's not a problem, right? So now this is less than equal to distance between fx and fxk plus distance between fxk and fy. This is less than epsilon, there is less than epsilon, total is less than 2 epsilon. Okay. So just this delta is okay, but here I make the balls very small balls
Very small.
covering the whole space. Compactness is, I had this. I did something extra. I took it with delta by 2. So I think this is good. Sorry for that. It just took a while. Continuous function and a compact set is uniformly continuous. Fine. Is that right now?
So actually we found one of the x case such that both x and y
both
is
will land
inside
delta.
the delta ball around that. Right.
Exactly.
Since we did that one, now distance of okay.
Yeah.
Okay, since they're inside, so it has to be, that distance has to be less than distance of fx to fxk and fxk to fy.
Same xk is used here. That's the whole point. Is same xk is used here. That's what I did.
Same xk is used.
Same xk is used. That's what we were looking for. Okay. So I think we got it finally. If x is compact and f is continuous, then actually it's uniformly continuous. All right. Okay. Good. I mean, I've taken too much time on that. There are a couple of small things that we need. Subramaniam, some question? Okay.
Yeah. No
Yeah.
question.
Yeah. Next, we introduce a little. We're almost done here. We just want to talk about, something like a little result here. Convergence of sequence of functions. If I look at a sequence of functions, Fn is considered for each on x to y or something, or x to omega, and for each n, Fnx probably has a limit. Okay. Right. Once again, for each x, I have to talk about for every epsilon greater than 0, there exists a delta which may depend on x. There exists an n which may depend on x such that n greater than equal to n implies the distance between f and x and fx in the second metric space is less than epsilon. That's convergent point-wise. But I want to talk about convergence on the whole space, what is called uniform convergence. Okay. We say a sequence Fn of functions on X. Okay. Maybe let Fn be a function from X d1 to omega d2. Okay. We say Fn converges uniformly to F on X and right. Your textbook used a different notation. I think I'll just use this notation. Fn converges to F. He said uniform limit of Fn is F. Okay, it's okay, not a problem. I say Fn converges to F as n tends to infinity. If for every epsilon greater than 0, there exists a capital N, a positive integer, such that distance between Fn x and Fx will be less than epsilon for all n greater than equal to n and for all x in X. Okay, the capital N is not going to depend on X anymore. So this is what uniform convergence is. Okay.
So basically,
Actually,
after a certain point, those two curves become the same. That's close to,
they're
essentially.
close to each other,
That's
right?
what yeah.
Yes, exactly. Uniform convergence. Actually, point-wise convergence and uniform convergence. If a sequence of functions are all continuous, we want to ask whether the limit function is also continuous or not. That actually depends whether this convergence is uniform or point-wise convergence. If the convergence is only point-wise, F need not be continuous. But if the convergence is uniform, F has to be continuous. So I would like to prove that if Fn, the sequence of functions Fn are all continuous and the convergence is uniform, then F is also continuous. Okay, here is the theorem. I should easily give you counterexamples in case when F is only converging point-wise. We can easily create examples. If Fn converges point-wise, the limit function need not be continuous. For example, let's take 0 to 1.
One example, you elaborate, I will suggest one thing. Suppose a stock price is taken as
Okay.
one function,
Okay.
and 50 days average is taken one function, 100 days function is taken one function, 200 days function is also taken one function. So certain of the functions may converge at some point. I don't know whether it relates to your idea.
We can give an easy example here. Let's look at this example.
Yeah.
This is half. Let's take half minus 1 by n and half plus 1 by n. Okay. When n is more than 2 or 3. Okay. So this is one function which goes 0 up to here, goes like that, and goes down, and this. Okay, if you take this sequence Fn, what is the limit of this sequence? And the limit of this sequence will be the following. It will be at half, it will always be 1, but everywhere else it becomes 0. Okay, there is the example. So this is the level 1. Okay, the function is defined like this, like that. And if you look at point-wise limit, on and after a certain stage, every one of them is becoming 0. Only at half it is 1. So the limit has become the following. What did the limiting function become? This limiting function became this. At half it is 1. Okay, everywhere else it is 0. There you go. The sequence of functions which converge pointwise to that. We can prepare this function, right? This is a sequence of functions. This is Fn. This is y equal to fx. Limit function is not continuous. Okay. But if the convergence is uniform, then definitely f has to be continuous. This is not a uniform convergence. What Yasodhara said is that actually, in some sense, both the curves are just coming close to each other in the limit, which is not doing. Okay. So let Fn x d1 to omega d2 be all continuous. And Fn converges to F uniformly. As n tends to infinity, then F is continuous too. So uniform convergence is much stronger, as we already see from the definition. Here is the counter example in the case of counter example. In case convergence is pointwise. Okay. So we'll prove this basically when Fn and F come very close to each other, right? The Fn is continuous. Continuity of Fn will be used to prove the continuity of F at a point. Okay, proof. Let x naught belong to x. Okay, and let epsilon be greater than 0. Okay, I want to produce a delta greater than 0 such that the distance between x and x naught less than delta implies distance between fx and fx naught is less than epsilon. Okay, now Fn converges to F as n tends to infinity. So therefore, there is a capital N, a positive integer, such that distance between Fn and F is less than epsilon by 3 for all. Distance between Fn and F3 means for all x. The distance between Fn x and Fx is less than epsilon by 3. Actually, for all, but in particular, Fn is good enough for me. Okay. Epsilon by 3. Also, Fn is continuous. This is true for all x in x. Okay. Since Fn is continuous at x naught, there exists again a delta greater than 0, such that distance between x and x naught is less than delta, implies distance between Fnx and Fnx naught is less than epsilon by 3. Now, if distance between x and x naught is less than delta, I'm going to look at the distance between fx and fx naught. And naught is less than epsilon. Okay, this is less than equal to distance between fx and fnx. And this is plus distance between fnx and fnx naught, and distance between fnx naught and fx naught. There you go. This is less than epsilon by 3. This is less than epsilon by 3. This is less than epsilon by 3. This is less than epsilon by 3 because distance between x and x naught is less than delta. I have mentioned that. You can put epsilon by 3 very well. Okay. So this is less than epsilon. Epsilon by 3, epsilon by 3. Therefore, f is continuous at x naught. Okay. This is true for every x naught. This is true. This is true for every x naught in x. Okay, done. Okay, sir.
Right.
All right. I just want to introduce another small notion, and maybe we will finish up there. In general, let xt be a metric space. Okay. Given any set A be a subset of X, define and X is an element in X, define dxa. Then we see the set A, and here is an X here. I want somehow amongst all the distances I can find, I want to find the smallest possible distance. Infimum. This is like this, and here is X, and I want this, something like that. Infimum distance between X and Y, where Y is in A. Okay. You can even define for A and B subsets of X, define distance AB to be infimum distance between A and B, where A is in A and B is in B. So I have a set A here and there is a set B here. I'm sort of looking for that infimum somehow or other. Okay. Here's a little lemma, not a really big one, which is one distance between X and A is same as distance between X and A bar. A bar is closure of A. Okay. That's one of the distance between X and A is distance between X and A bar. Okay. And two, if distance between X and A is 0, if and only if X has to be in A bar. And finally, distance between X and A and Y and A, these are numbers. This is less than equal to distance between X and Y. Okay. We have to feel that this is what exactly what it is. I can write the proof here for the first one, let's say. Obviously, A is contained in A bar, so dx A bar should be less than equal to dx A. Okay. I want to show that dx A bar is greater than equal to dx A. If not, what happens? If actually, suppose we want to show distance between X A bar is greater than equal to distance between X A. Suppose not. Suppose it is less than. Distance between X A bar is strictly less than distance between X and A. Okay. I'm going to choose some number R and S between the two things. Let R comma S be real numbers. How I took distance between X A bar is less than R, less than S, less than dxa. Okay. Right. What happens now? This is actually infimum of all distances between X and A bar. So if I take something more than it, definitely there is one element inside this whose distance will be less than r. Okay, because this is infimum. So there exists a y in a bar such that distance between x and y is strictly less than r because this is infimum. Okay. Now y is in the closure, and there is this. This is dx a bar. This is dx a. I have r here and s here. There's a little difference here. Maybe some r s minus r is some delta. So if I take a ball of radius s minus r by 2, because y is in a bar, every ball of radius, any small radius around y should intersect a. So the ball of radius s minus r by 2 centered around y should intersect a. Is that right? That means there should be an element x in a. There exists a x in a such that distance between, oh, that already x is there. So x dashed in a, thus the distance between x dashed and y is less than s minus r or s minus r by 2. I think s minus r is good enough. Which means I have found out the distance between x and y, x and x dashed is less than this distance between x and y, and the distance between x dashed and y, but distance between x, y is less than r, and this is less than s minus r. Together it is s. Oh, I see. I found an x dashed in a, so the distance from x to x dashed is less than the infimum. That's the contradiction. Okay. So I don't think this will be less than that.
Yeah.
So what you are saying is that, yeah, I hope you understood that now. This is a contradiction.
Yeah.
So this is not
Yeah,
going to work out. I'll get this to them. Okay.
Yeah, the closest point should be on the boundary of A, basically.
Exactly.
That's
I think
all
that's
we're
what.
trying to,
Yeah.
that's what you're trying to take advantage in proving this. Yeah.
Exactly.
Yeah.
Exactly. Okay. I think this is also same thing in that way. Okay. Right. This is what exactly say going to say the same thing here. You know, because if dxa is 0, I can find a sequence of elements in A, which so that the distance between x and xn should tend to 0. But
10
that
to
means xn
0.
tends to x. But that means xn tends to x. That means x has to be in A bar. Okay. Other way around is nothing because yeah. Okay. So that follows that. And this is also simple. Okay. So third one I'll prove. Third one is also not much. If I take for every a in a, distance between x and a is less than between less than equal distance between x and y plus distance between y and a. Okay. So therefore, infimum among all a will give me dxa. Infimum among all y, all a will give me d
DYB.
ya. So this implies dxa is less than or equal to dxy plus dya. Infimum over a, over all a makes it dxa, over all a makes it dya. So this dxy is just sitting there ideally. That would imply distance between x and a minus distance between y and a is less than or equal to dxy. By the same token, I can reverse it and say negative of this is less than or equal to that. I can start dya less than dxy plus dxa. So I can get the other inequality also. It means modulus is less than or equal to that. Okay?
Right.
So that takes care of it. Similarly, we can prove distance between YA minus distance between XA is less than equal to distance between XY. So there you go. I proved this. Okay. Now, I probably will not do it now anymore. I have some other engagement. What I have to say is, in case if I have a compact set, and there is an X here, and you have the compact set here, if you look at dxk, which is infimum over dxy, that infimum will be achieved by certain point y naught in k. So there is a point in the compact set which will be nearest to x. We are just talking about infimum. We are not saying that there is an element y in A where dxy will be dxa. We're not saying that this infimum is achieved by any point in A. But in case of a compact set, then the infimum will be achieved. Proof is already very easy because the infimum is achieved by a sequence of yns in the compact set. So d yn x will tend to that infimum alpha is infimum is alpha xa xk. However, these yns are within k. Being a compact set, you have a convergence subsequence. So that convergence subsequence actually converges to some y naught. Then you can see that this converges to dy naught x. And so this dy naught x will be dxk. That means there will be y naught. That's what you have to say. Okay. So in the case of a compact set, I can do that. Indeed, if I have two compact sets like that, I should be able to find the infimum between them to be achieved by an x naught here and y naught here, which I cannot do it in general, which I cannot do in general. Okay. For example, if I have two open balls, there's an open ball and here is an open ball. The smallest distance is this distance, but that is not achieved either by this or by that, because these are open balls. If they're compact sets, you have no escape. This is what the essence of what I wanted to say. You can read the rest of the small lemmas over there and finish that. So maybe we'll just say we're done here. Next lecture onwards, we will start complex analysis proper. Okay. The introductory part I want for topology is reasonably done, and we will start the theory of complex functions. Tomorrow I cannot do because I'm quite swamped here. If you guys okay, we'll meet Monday. Okay.
Mondays. Okay.
Monday is so I anything that is left out here, you can read it from the textbook. I'm just following the textbook only, and so we'll start afresh with the functions of complex variable. I'm quite excited to actually do the theory myself.
Okay.
That's all.
Okay. Sounds good.
Bye everybody. Bye Subramanian.
Thank you.
See you tomorrow. In a couple of days. Actually, Subramanian is coming to Vizag. Maybe tomorrow itself is coming.
That's what he was. We were talking before you.
Tomorrow evening, by evening, I'll reach there.
Okay, we'll talk about it. Okay. All right, sir. Bye.
All right.
Take care.
Thank you.
Thanks.
Bye.